Hi, and welcome to the fourth tutorial video for this term. This tutorial introduces some methods to solve problems by using the law of conservation of energy. The first problem states, determine the velocity of the block A of weight WA if the two blocks are released from rest and the block B of weight WB moves a distance d up the incline. The coefficient of kinetic friction between both blocks and the inclined planes is μk. Here's my recreation of the problem. Since it's a pulley problem, we will need to assign some measurements to the string lengths so that we can use the conservation of string principle. I'll call these two lengths SA and SB. The total length of string is 2SA plus SB, and if we take the time derivative, then we find this relationship between the block velocities. Note that since we're measuring SA and SB as the length from the middle pulley, this relationship assumes that a positive velocity is one where the block is moving down the ramp, since that would increase the length S. You might be wondering about this little section of string, and why I didn't include it in the measurement. I didn't include it because it's simply a constant length, so it disappears when we take the derivative anyway. So, how do you know when a problem is more easily solved using energy methods? One hint, as we'll see in later problems, is if the path of motion either isn't given or is pretty complicated. However, that doesn't really apply in this problem. Instead, with practice you'll find that certain problems have a clear energy relationship between the initial and final states. For example, the change in height of each object will be known, and maybe the direction of velocity isn't as important as the speed. It's a little more subtle, and it's hard for me to give a concrete guideline, but with practice you'll begin to see it too. That aside, let's come back to this problem. You can see that for every unit distance that block B moves up the ramp, block A moves down its side by half as much. Let's label D according to the problem statement, and we'll also label D over 2 next to block A. Next, I'd like to introduce some key energy terms that we will need. The expression for gravitational potential energy is mass times gravitational acceleration times h, where h is the height of the object above a fixed reference line. The expression for kinetic energy is 1/2 times m times v squared, where v is the speed of the object. These expressions for gravitational potential energy and kinetic energy are just the measure of the energy at some fixed point in time. So to find the change in energy, you would subtract the initial energy from the final energy. Finally, work is given by force times distance. In actual fact, work is the dot product, which you should know from linear algebra, of the force and displacement vectors. Okay, let's move on by writing the conservation of energy equation. For simple dynamics problems like these, we can say that the work in minus the work out is equal to the total change in gravitational potential plus the change in kinetic energy. You can think of the left side as the total net work entering the system, which changes the overall energy of the system that's on the right side. After filling in all those terms, we can see that the force of friction on blocks A and B is on the left side. Since the force of friction is opposite the direction of motion, the work is negative. In other words, friction is like work going out of the system. The friction force acting on A is multiplied by d over 2, since that's the distance that block A moves, and similarly, the friction force acting on B is multiplied by d. The change in gravitational potential of each block is the weight, or mg, times the change in height. Block B raises in height by d sine theta 2, and block A lowers in height by d over 2 times sine theta 1. The signs are positive and negative, respectively. Lastly, we have the change in kinetic energy. The initial kinetic energy is just 0 since the blocks are released from rest. The final kinetic energy is 1/2 mv squared for each block. I'll just simplify the equation a little bit, and you can see that in order to solve this for the final speeds, we're going to need the normal force acting on each block, NA and NB. So, we draw some free body diagrams and sum up the forces acting in the normal direction for each block. We know that those forces should sum to 0 since the block doesn't accelerate in the normal direction. That lets us find the normal forces as WA times cos theta 1 for block A and WB times cos theta 2 for block B. Now, we're left with these two equations with two unknowns, which are VA and VB. Solving those equations gives us the answer of VA equals 0.233 meters per second and VB equals negative 0.466 meters per second. Now for problem 2. It states, the roller coaster car has a speed VA when it is at the crest of a vertical parabolic track. Determine the car's velocity and the normal force it exerts on the track, when it reaches point B. Neglect friction and the mass of the wheels. The total weight of the car and the passengers is W. So we have a known curved path which this roller coaster follows, and we're interested in the velocity and normal force when it's at point B. We know to use energy methods here since the path between the points A and B is somewhat complex, so energy methods make our life a lot easier. Just like before, we can write out the conservation of energy equation. We can expand it out, and we can see that we pretty much know everything in this equation already. We can find YB and YA from the path equation shown in purple, and VA is given. This results in an answer of VB equals 34.435 meters per second. Next, we use a free body diagram to solve for the normal force. We can sum up the forces acting in the normal direction, and we know that the normal acceleration is VB squared over rho B, since it's a centripetal acceleration. The unknowns in this case are theta and rho at point B. We can find them using these expressions, which I showed in a previous tutorial. We can find the derivative of y, and then the second derivative, and then sub in b for x. Now we have everything we need, and we can just plug and chug to find that the normal force is 151.7 newtons. Lastly, we have problem 3. It states, the Raptor is an outside loop roller coaster in which riders are belted into seats resembling ski lift chairs. Determine the minimum speed V0 at which the cars should coast down from the top of the hill so that passengers can just make the loop without leaving contact with their seats. Neglect friction, the size of the car and passenger, and assume each passenger and car has a mass m. The car starts with a velocity of v0 and travels to reach the height of the loop here. We should use the height of the loop, since that's the point where gravity is pulling the rider directly away from their seat, and the velocity of the car is at its lowest, which results in the lowest possible centripetal acceleration. At that point, the velocity is v1 to the left. Let's draw a free body diagram and sum the forces in the normal direction. In dynamics questions, whenever the question states that contact is barely lost or on the verge of being lost, that means that the normal force is equal to 0. So, we set n equal to 0 and cancel out the mass term. That gives us this expression, which tells us the velocity at point 1, which is needed to have the passengers on the verge of losing contact with their seats. Next, we can use the energy equation just like before and make the necessary substitutions. We can rearrange for v1, and now we have an equation that links v1 to v0. We can just plug and chug to find that v0 is the square root of g times 5 rho minus 2h. This question was pretty quick, but it combined a lot of different concepts. To solve it, we needed to recognize that the point of maximum height in the loop is where the riders were most likely to lose contact with their seats. So that's it for today's video. As always, you can contact me at this email address if you have any comments or questions. Thanks for watching, and I'll see you in the next video.